Hello, and welcome to our discussion of solving the wave equation with the Fourier transform. We will look at the initial value problem, utt equals c squared uxx, for x in the reals and t positive. This is the wave equation on the real line, together with the initial conditions u of x0 equals phi of x, and ut of x0 equals psi of x for given functions phi and psi. And we will apply the Fourier transform to this initial value problem, solve the resulting Fourier side differential equation, and then try to learn something about u from this formal solution. Not every single step that we take here will be rigorously justified. In particular, we'll start out by assuming that we actually have a solution to the problem and then figuring out a formula for it. But as with our work on the heat equation and other ODEs and PDEs, the idea is that the Fourier transform will help us guess or get a candidate for a solution to what could otherwise be an inscrutable PDE. Let's begin. We take, as usual, the Fourier transform in x in our spatial variable, because the Fourier transform works when you have a function defined on the whole real line, and here x is in all the reals while t is only non-negative. And so on the Fourier side, we have u hat tt at kt equals minus c squared k squared u hat of kt. Here k is real and t is greater than 0, with initial conditions u hat of k0 equals phi hat of k, and u hat t of k0 equals psi hat of k. So now we can think about the differential equation on the Fourier side as moving in time. We're taking derivatives with respect to time, and k is now a real parameter. So for each real number, we have a different differential equation to solve. And as usual, we got this differential equation by using the way the Fourier transform interacts with spatial derivatives and by differentiating under the integral. For this to work out, it seems that we would need phi and psi to be in L1. After all, if they're not in L1, their Fourier transforms couldn't be defined. Let's start by working with the ODE. If we put everything on one side of the equal sign, we have u hat tt plus c squared k squared u hat equals 0. So remember, c and k, from the point of view of this ODE, are fixed parameters, and the ordinary differential equation is taken with respect to time. So this is a second-order constant coefficient differential equation. And if k is not 0, then because we always assume the wave speed c is non-zero, we have c squared k squared positive. So the general solution is u hat of kt equals alpha of k cosine of ckt plus beta of k sine of ckt. Here alpha of k and beta of k are constants that depend on k, because remember, for each different constant k, I have a different differential equation. Now let's figure out what these constants have to be. If we have k not equal to 0, let's look at the initial conditions from t equals 0. What do we have? We had phi hat of k equals u hat of k0. Well, from this formula from differential equations theory, what is u hat of k0? This is just going to be alpha of k. Because if I plug in t to the formula at the top of the screen, the cosine becomes 1 and the sine becomes 0. So this tells me immediately what alpha of k has to be. It's phi hat of k. Now let's differentiate the formula at the top of the screen with respect to t. U hat t of kt is minus ck alpha of k sine of ckt plus ck beta of k cosine of ckt. Got a lot of letters there, but just remember I'm differentiating with respect to t. And so that tells me that psi hat of k is u hat t of k0 from my initial Fourier work. And then if I plug in t equals 0 to this derivative, I get ck beta of k. So altogether, I can solve for beta of k as psi hat of k over ck, and then u hat of kt, this rearranges to become cosine of ckt phi hat of k plus sine of ckt divided by ck psi hat of k. I just flip the order of some factors around here. And so it seems like on the Fourier side, I'm done, at least for k not equal to 0. I've written u hat of kt entirely in terms of things that I know, the wave speed c, and the transforms of the initial data phi and psi. Let's look at the k equals 0 case for a moment. In this case, going back to the previous slide, the initial value problem that I get for the Fourier transform is u hat tt of 0t equals 0, u hat of 0, 0 equals phi hat of 0, u hat t of 0, 0 equals psi hat of 0. Just plugged in k equals 0 in a lot of places. And if you just integrate this differential equation twice, you get u hat of 0t equals psi hat of 0t plus phi hat of 0. You might think this is a little weird. I have seemingly two very different formulas for u hat of kt. One when k is not 0 in the middle of the screen, and the other for k equals 0, the simple linear formula in t. These really are the same things. First of all, if you fix t and take the limit as k goes to 0 of u hat of kt, when k is not equal to 0, this is the limit as k goes to 0 of cosine of ckt phi hat of k plus sine of ckt over ck psi hat of k. And so that looks like it should be the limit of phi hat of 0 plus the limit as k goes to 0 sine ckt over ck psi hat of k. Remember one of our favorite limits from early calculus. The limit as theta goes to 0 of sine of theta over theta is equal to 1. And so the limit as k goes to 0 of sine of ckt over ck is t times the limit as k goes to 0 of sine of ckt over ckt, which is just t. So the formula for u hat of kt when you have k not equal to 0, if you take the limit as k goes to 0, you get back the formula for u hat of 0t, phi hat of 0 plus t psi hat of 0. This is not really surprising. Our Fourier theory, one of the second mapping theorems on the Fourier transform that we had, said that u hat of kt should be continuous in the Fourier variable k if u of xt were nice enough. The point is that we can just think about this formula u hat of kt equals cosine of ckt phi hat of k plus sine of ckt divided by ck psi hat of k. Even when k equals 0, we'll just agree to call that phi hat of 0 plus t psi hat of 0. So now the question is, can we invert this transform? I know what u hat of kt is for all k. I want to invert it and get back u of xt. So let's look at the two terms separately. What's the inverse Fourier transform of cosine of ckt times phi hat of k? Remember, we're taking the transform's inverse with respect to the Fourier variable k. T and c are now parameters. You can't use convolution here even to get a formal identity because cosine is not an L1 function. So let's complexify. Cosine of ckt times phi hat of k from the complex form of the cosine is e to the I ckt, ict, plus e to the minus I ckt divided by 2 times phi hat of k. Right, just complex form of the cosine of ckt. And that turns into e to the I ckt phi hat of k over 2 plus e to the minus ict over phi hat of k times phi hat of k over 2. This may not look any better, but remember that when you have the Fourier transform in k and e to the I times k times something out in front, there is an identity you can use. If we put sd on f at x to be f of x plus d, the shift by d operator, then sdf hat of k is e to the ikd f hat of k. So we have here e to the I ckt and e to the minus I ckt. These are related to shifts. E to the I ckt phi hat of k, if I just factor this a little better, it's e to the I times ct times k phi hat of k. So that's shift by ct on phi hat at k. And so if phi is a sufficiently nice function, say it's continuous and piecewise continuously differentiable, then I expect that the inverse Fourier transform of e to the I ct phi hat of k over 2 at x is just shift by ct on phi at x over 2, or phi of x plus ct over 2. So now it seems I have to assume a little more about phi. It's not just in L1, but it's also continuous and piecewise continuously differentiable. But this means I'm able to invert that first term in the cosine of ckt on phi hat of k. And then I invert the second term in the same way. So the inverse Fourier transform of cosine of ckt phi hat of k at x should be phi of x plus ct plus phi of x minus ct over 2. Now I need to study the second term, inverse transform of sine of ckt over ck times psi hat of k. What is this? Well, let's define an auxiliary function. Chi of xt will be 1 if the absolute value of x is less than or equal to t, and 0 if the absolute value of x is greater than t. This is sort of an indicator function. And then we know that if I take the Fourier transform of psi in the x slot, so I get chi hat of kt, this turns out to be square root of 2 divided by pi times sine of tk over k. This was a transform that we calculated earlier in our Fourier study. So what does this tell me? The factor that I care about in this inverse Fourier transform, sine of ckt divided by ck, is really 1 over c times square root of pi over 2 chi hat of kct. So what does this say? The inverse transform of sine of ckt over ck times psi hat is 1 over c times root pi over 2, inverse transform chi hat of kct times psi hat. So I have the inverse Fourier transform of chi hat times psi hat. Inverse Fourier transform of two hats calls for convolution. Now, convolution is a little weird here because I have to assume so many wretched hypotheses on psi, and also sine of ckt over ck isn't exactly absolutely integrable, which was part of one of our convolution hypotheses. Here's the fun part. We're not going to worry too much about those hypotheses. We're just interested in a formal solution, in a candidate for trying to solve the wave equation. So we're going to proceed here as though we could use all our convolution techniques without worrying about the hypotheses. What does this become? Well, I keep my factor 1 over c times root pi over 2. I have to multiply in a new factor of 1 over root 2 pi. And then the inverse transform of chi hat times psi hat is chi convolved with psi evaluated at x. And if I multiply through the constants a little, this becomes 1 over 2c times chi convolved with psi. And to be clear, remember chi depends on two variables, the x slot and the t slot. I'm convolving chi with psi in the x slot of chi. So let's work that out. Chi convolved with psi at x. I could also flip the order of my factors around and say that's psi convolved with chi. Remember, convolution is commutative. So that's the integral from minus infinity to infinity of psi of x minus xc, chi of xc ct dxc. So xc is the variable of integration. X, c, and t are parameters that are fixed inside the integral, and psi and chi are functions. Remember what chi does. Chi is 0 outside the interval minus ct to ct. So this integral becomes the integral from minus ct to ct of psi of x minus xc. Or if you prefer, you could change variables. So this becomes the integral from x minus ct to x plus ct of psi of u du after a quick substitution. So let's put it all together. U of xt from the Fourier work should be the inverse transform of cosine of ckt phi hat plus inverse transform sine of ckt over ck times psi hat. And looking back to the previous slides, this becomes phi of x plus ct plus phi of x minus ct over 2 plus the integral from x minus ct to x plus ct of psi of u. So gloriously, we have a formula for u that only depends on the wave speed parameter c and the initial data phi and psi. We could even rewrite this a little further as phi of x plus ct over 2 plus the integral from 0 to x plus ct of psi plus phi of x minus c2 plus the integral from x minus ct to 0 of psi. So I just split up the fraction and the integral. And I could call this f of x minus ct plus g of x plus ct. So let's call the stuff inside the left parentheses g of x plus ct, and the stuff inside the right parentheses f of x minus ct. And we'll see in the next video that this is a really useful way to compress the formula for the solution to the wave equation. Now let me emphasize this is a formal solution, and whenever we use the word formal in this class, and we've used it a lot before, we mean something that is symbol pushing and useful, but quite possibly unjustified and not rigorous. We assumed that we had a solution in the first place, and that everything was nice enough that we could do all our Fourier business. Sometimes we didn't always justify all those Fourier multiplications and manipulations, and we got a nice formula in the end. Now our task is going to be to see, one, is this formula differentiable, and does it differentiate into the wave equation and solve the wave equation? And then, can we always write a solution to the wave equation as this formula? Can we prove this now rigorously using the intuition from the Fourier transform? And yes, we shall, and we'll do that in the next video.